Welcome to the second episode in part 1 of our 3-part series Adventures in Op-Amps, where we explore how to make useful amplifiers out of op-amps. In this episode, we will find out one of the reasons chip designers make op-amps that have very high amplification gain, and how a concept called negative feedback can be used to mitigate the clipping that happens to the output of op-amps due to that very high gain. There are many reasons why op-amp designers build them with very high gain. We will address one of these reasons now, but we'll also revisit the topic in part 3 of our adventure when we tackle more advanced op-amp concepts. Designing op-amps with very high gain seems counterintuitive, especially when we realize that most users of amplifiers need an amplification gain in the range of 10 to 1,000 times the input signal. The key word in the last sentence is range. Every type of electronic product requires a slightly different amplification ratio, but creating an op-amp design for every type of electronic product is not a desirable thing from a financial perspective. Makers of op-amps want to create one device design that gets used in a wide range of electronic products. So ideally, they want to create a single design for op-amps that has a fixed gain factor and that we can then modify its gain to whatever value is needed. Such modifications should be done using cheap components like resistors, which when attached to the external terminals of the op-amp would produce an amplifier whose gain is related to the values of these resistors. We want the gain of these amplifiers to depend solely on the resistor values so that the end user will have full control of the resulting amplifier gain. So here we have two examples of amplifiers that each use the same op-amp design. However, their resulting gain is dictated solely by the values of the two external resistors. In the example shown here, we're able to control the amplifier gain by connecting the resistors in a special way that we will describe soon. Moreover, we're able to select the values of the resistors in a way that results in a reasonable amplification factor of 100 or 40. Such reasonable amplification factors would not cause the output waveform to be clipped. The next logical question is, how do the two resistors control the value of the gain in amplifiers like this one? There are two essential design concepts that work together so that the amplifier's gain is totally controlled by the resistors. The first concept is called negative feedback, which is the process of having the output of the amplifier be connected back into one of the inputs of the op-amp. Negative feedback is a very key concept in engineering. Not only does it help us build amplifiers out of op-amps, it is also used to control the speed of electric motors, to guide the flow of data traffic in the internet, and even to train artificial intelligence networks like chatbots. The need to use negative feedback around op-amps clarifies the reason for having two inputs for the op-amp. One of them is needed to create this negative feedback path, while the other one can be used for our input signal. The second design concept needed to ensure that the amplifier's gain is totally controlled by the resistors relates to the internal gain factor of the op-amp. It needs to be extremely high. The higher the better. Ideally, we would like it to be infinite. And while infinite gain is impossible to engineer, op-amp designers have been able to regularly create op-amps with gain factors of 100,000 or more. So now, let's see how these two concepts allow us to use external resistors to control the gain of the overall amplifier. To understand how these two concepts produce practical amplifiers, we must first learn about the op-amp's input versus output curve, which we will draw on this graph. On the x-axis, we will represent the result of subtracting the voltage on the negative input terminal from that of the positive input terminal. Looking inside the op-amp, we see that the x-axis represents the voltage at the internal point in the op-amp right after the subtraction happens. So if the positive input has higher voltage than the negative input, we would be on the positive side of the x-axis, and vice versa. The y-axis is much simpler. We just plot the voltage at the output of the op-amp on the y-axis. That output voltage is usually called Vout or V sub O. Now, because the gain of the amplifier is so ridiculously high, whenever there is any significant difference between the input voltages, the resulting multiplication by a very high gain would require the output voltage to be at a level that is well beyond the supply voltage. But because the op-amp can never produce a voltage beyond its supply voltage, then for all these cases, the op-amp will just produce an output that is approximately equal to the positive supply voltage, which is Vs+. We notice that because of the massive gain of the op-amp, this will happen for almost all values of the positive axis. It also means that the op-amp will produce an output that is approximately equal to the negative supply voltage, that is Vs minus, for almost all negative values on the x-axis. Because the changes in the value of the x-axis do not really change the op-amp output in these two regions, we call them the saturation regions. All this implies that there exists a very small region on the x-axis where the difference between the two input terminals is so small that when that small difference is multiplied by the massive op-amp gain, the resulting number is within the range of the supply voltages of the op-amp. For that tiny region, we have a proportional relationship between the difference of the two input signals and the output voltage. That proportionality relationship is expressed by the almost vertical straight line going through the origin. This line represents the tiny region where the op-amp is doing proportional amplification. The slope of that line is the value of the op-amp's gains factor, and so we can formulate a simple straight line equation that describes the relationship between the x and the y variables. Because this amplification region is well described by a straight line, we call it the linear region. Next, we will dive into the width of that linear region on the x-axis. It is extremely tiny and narrow, and yet that is the region that we will need the op-amp to work within so that the output is not clipped by the limitations of the supply voltages. To illustrate the narrowness of the linear region on the x-axis, let's continue with our typical op-amp that has a gain of 100,000 and is supplied by a plus 15 and minus 15 volts. These would be the output voltages when the op-amp operates in the two saturation regions. To find the width of the linear region on the x-axis, we want to find the x-axis value for the 2 points highlighted by the red circles. To do that, we just set the value of the output voltage in the linear region equation to be equal to the supply voltages, and we solve for the value of the x-axis that would produce such an output voltage. When we plug the values of the gain and supply voltages into the linear region equation, we find that the linear region would start at an x-axis value of minus 0.15 millivolts and end at an x-axis value of 0.15 millivolt. The grand total of the range for the linear region on the x-axis is 0.3 millivolts from start to end, and that is a ridiculously small range. For example, the typical Wi-Fi signal or FM radio signal will produce well over 1 millivolt of signal in the receiving antenna. That is already well beyond the range of the op-amp's linear region, and therefore beyond what this op-amp can amplify without clipping the output signal. And yet, if we want to use the op-amp as an amplifier, we must keep the difference between the two inputs within that very narrow range so that the output voltage remains proportional to the input voltages. The problem, of course, is that we have no control whatsoever on the values of the input signal. It may easily go beyond this very narrow region, but that is also a very nice little engineering problem to solve, and we will do that in the next slides. Now recall that in the previous episode we encountered a configuration where the input signal was connected to the positive terminal and the negative terminal was grounded. This configuration did not work well because every time the faint signal went beyond the very narrow linear region on the x-axis, the op-amp entered the saturation region. And every time that happened, the op-amp stopped amplifying and the output signal got clipped to the level of the supply voltages. A potential solution to this problem would rely on the fact that the op-amps amplify the difference between the two terminals. Think about what would happen if we took our configuration that does not work so well, but instead of connecting ground to the negative terminal, we connected another signal that looks just like the faint input signal, but whose amplitude was just a little tiny bit smaller than the input signal. For example, let's assume that the new signal is exactly the shape of the faint input signal multiplied by 0.9999. That's 4 nines. In that case, the difference between the two signals would have the same shape as the input signal, but an extremely small amplitude. Actually, it'll be 10,000 times smaller than the input faint signal. Now, if we multiply that different signal by the gain of the op-amp, the resulting output would be only 10 times the amplitude of the original faint input signal. Great! We've just figured out a potential way for amplifying our input signal without clipping it. All we have to do now is to generate that slightly small input signal in a reliable manner. Luckily for us, the problem was solved in 1927 by an engineer named Harold Black, who was solving the clipping problem for amplifiers that used vacuum tubes instead of op-amps. Harold Black solved this problem by inventing the concept of negative feedback, and so negative feedback is what we are going to look at next. Harold Black realized that if the amplifier does a good job and does not clip the output signal, then the output signal will have the same shape as the input signal. Therefore, we can use the output signal as the source for that slightly attenuated signal that we want to connect to the op-amp's negative input terminal. All we have to do is connect the output signal through a feedback circuit that reduces the amplitude by a fixed amount, and then connect the output of that feedback circuit to the negative terminal of the op-amp. This type of feedback is called negative feedback because the output of the amplifier is connected to the negative input of the op-amp and is subtracted from the input faint wave that appears on the positive input of the op-amp. It is this process of subtracting the feedback signal that makes the system a negative feedback configuration. This simple concept assumes that the output wave appears on the amplifier output almost instantaneously when the input signal is applied to the input positive terminal. Luckily for us, electronic amplifiers have an almost zero propagation time from the inputs to the outputs, and so the shape of the output signal is an almost instantaneous replica of the input signal. The simplest feedback circuit is just a zero resistance wire that conveys the output voltage directly to the negative input terminal. A wire with zero resistance is an electric short circuit. But what amplification would we get with this simple feedback circuit? There is a mathematical way of answering this question, but then there is also a more intuitive, qualitative way of also understanding it. And in the next episode of part 1 in our adventure, we will start off by exploring the qualitative intuitive understanding of how negative feedback works before we delve into the mathematics that describe the result of applying negative feedback to the op amp.